TiDAR, think in diffusion, talk in autoregression. Here's the core idea in plain terms. Diffusion models can brainstorm many tokens in parallel, super fast. Autoregressive models speak one token at a time, but with great accuracy, because each token depends on what came before. TiDAR combines these strengths. It uses diffusion to think ahead in parallel, then uses an autoregressive step to finalize what actually gets said. The promise is simple but powerful. AR-level quality without paying the slow, one token at a time cost. Why is this hard? AR models are great at language because of their causal flow. Each new token predicts the next, grounded in the exact context so far. But they're slow, one token per step. Diffusion can decode many tokens at once, which is way faster, but pushing diffusion into left-to-right decoding, to mimic AR, kills its parallel advantage and still hurts quality. Speculative decoding tries a compromise. A small model drafts, a big model verifies. But the small model often drafts poorly, wasting verification time. The big question is, can we get AR-level quality while keeping the massive parallel speed of diffusion? That's the gap TiDAR aims to close. TiDAR's trick: separate thinking from talking. It drafts multiple candidate tokens in parallel using diffusion, the thinking phase, then locks in the final outputs with a lightweight autoregressive pass, the talking phase. Crucially, it does both in a single forward pass using structured attention masks. Think of the mask as traffic rules. Some positions can look ahead to collaborate during diffusion, while the AR part only looks left to keep causality. Because modern decoding is memory-bound, carrying extra token slots through one pass costs little extra time, so TiDAR exploits that free compute to beef up both drafting and verification without extra latency. It's a standalone, serving-friendly design that keeps overhead low and throughput high. What does it achieve? At 1.5B and 8B scales, TiDAR beats speculative decoding in real measured throughput and outperforms prior diffusion LMs like Dream and Yada on both speed and quality. The key enablers are parallel drafting and sampling plus exact KV cache support, so it slots into standard serving stacks efficiently. Most impressive, it closes the quality gap to strong AR baselines while producing 4.7x, 5.9x more tokens per second. In other words, you get the reliability of AR with the speed you'd expect from diffusion without juggling two models or complex multi-pass orchestration. Modern LLMs thrive on GPU scale, but during decoding AR models are memory-bound. Time is dominated by moving weights and KV cache, not math. And since AR emits exactly one token per step, GPUs sit underutilized at low batch sizes. Diffusion LMs promise a fix: predict many tokens in parallel per pass. The catch? As you parallelize more, quality typically drops. Best quality often comes from the most AR-like, one-step-at-a-time behavior. The author's move is to stop treating this as either-or. Use diffusion to explore multiple plausible futures quickly, then let a causal, AR-style mechanism finalize which tokens actually count. That way, you ride the hardware efficiently without sacrificing linguistic fidelity. Here's the system's intuition. Decoding is memory-bound. Loading weights and KV cache dominates runtime. If you can process multiple token slots in one forward pass, they share the same loaded weights and cache. That means extra token slots come almost for free until you hit the compute-bound region. Diffusion LMs naturally exploit this by predicting several positions at once. The paper calls these extra positions free token slots. You're already paying to load the model, so you might as well carry more tokens through the pass with little latency penalty. Think of a bus you've already rented. Adding a few more passengers doesn't cost more fuel if the bus was going anyway. But there's a quality tension. Masked diffusion models often perform best when you denoise strictly one token per step. As you increase parallelism, predicting many positions together, the model's guidance gets noisier and local consistency can suffer. That's why pure diffusion decoding struggles to match top AR quality. TiDAR acknowledges this trade-off and designs around it. Parallelize where it's cheap and helpful. Drafting. Then reintroduce strict causal verification right away, talking, so you preserve the crispness of AR without throwing away diffusion speed. Here's the core tension. Diffusion LLMs can think about many tokens at once, which is great for speed, but that parallelism often hurts quality. Why? Because when you try to guess several tokens simultaneously, you slip in independence assumptions that ignore the tight left-to-right dependencies language has. That's why strong open-source diffusion LLMs like Dream or Lada still lag top autoregressive AR models on overall quality. AR models commit one token at a time, always conditioning on everything generated so far. It's slower, but it lines up perfectly with how text unfolds and keeps decisions consistent. So the modeling difference is fundamental. AR is a precise chain of conditional choices. Diffusion is a broad parallel brainstorm. The rest of the paper is about getting the best of both worlds. AR's chain factorization is the gold standard for language quality. Think of it like writing a sentence word by word, each word chosen with full knowledge of everything before it. This structure naturally captures agreement, style, and long-range constraints, because every next token is scored with maximum context. The downside: you only generate one token per step, so GPU cores sit idle and throughput suffers. Still, this conditional chain is why AR feels coherent. Errors are less likely to snowball because the model constantly reevaluates with the freshest context. The paper will leverage this reliability for final decisions, while offloading parallel brainstorming to diffusion. Diffusion models sample by gradually denoising a rough draft into a clean prediction. In language, that means you can propose many token possibilities in parallel by treating them like noisy latent guesses and repeatedly refining. The big win is within-step parallelism. Lots of tokens can be refined together in one forward pass. But unless you're careful, those proposals don't fully consider each other's interactions, because the method tends toward marginal per-token views rather than a tightly coupled chain. Intuitively, diffusion is saying, let's guess a bunch of slots at once and iteratively make them less noisy. That's awesome for speed. The catch is that joint linguistic constraints, like ensuring a verb agrees with its subject several words earlier, can slip through the cracks if each token is treated too independently. So diffusion is excellent for fast parallel proposals, but without extra structure, it won't match the causal, context-rich commitments of AR. The paper's idea is to let diffusion do the fast brainstorming, while AR makes the final, context-faithful call. If you decode just one token per step with diffusion, you preserve quality better because each next denoising step conditions on the last committed token. But when you try to decode K tokens at once, you effectively treat them as independent, like filling multiple blanks simultaneously without letting them talk to each other. That independence is where quality drops. You can't enforce subtle cross-token constraints in one shot. It's the classic parallelism for quality trade-off. So single-token diffusion steps behave more like AR and stay accurate, but go slower. Multi-token steps go faster, but risk incoherence or blandness because they ignore the joint structure of language. That product of marginals phrase just means score each token in the batch independently and multiply. It's like grading each blank in a sentence without rereading the whole sentence after you fill any one blank. This is computationally convenient, great for parallel hardware, but it underestimates how much tokens constrain each other. In natural language, One choice often rules out others several positions away. When the model treats predictions as separate, it can choose locally plausible words that don't fit together. That's the technical reason why parallel multi-token diffusion steps can drift in quality. If you force diffusion to go strictly left to right, decode one token at a time, and use a training mask that hides the future, uniform suffix masking, diffusion essentially collapses into autoregression. That's insightful. It shows AR's quality comes from its strict causal factorization and conditioning, not from a particular loss alone. But it also defeats the purpose of diffusion speed. So the goal isn't to turn diffusion into AR, it's to strategically use diffusion where it shines, parallel drafting, while preserving AR's strengths when making final commitments. So the dream setup is compute with diffusion to get lots of ideas fast, but keep AR strong, context-aware decision-making for the final picks. Parallelism for brainstorming, causality for commitment. That means we need a model that can access both distributions, diffusion-style marginals for proposing many plausible tokens at once, and AR-style chain probabilities for choosing the best next token when it really counts. The rest of the method is about coordinating these two modes cleanly within a single forward pass. Meet TiDAR. Think, then talk in one shot. In each generation step, the model splits the sequence into 3 regions. 1, the prefix you've already accepted. 2, the tokens proposed in the last step that now need a final verdict. And 3, a fresh set of pre-draft proposals for the next step. Here's the flow. First, reuse the KV cache for the accepted prefix, no recompute. Next, use AR to judge last step's proposals via rejection sampling. The chain-aware AR head acts like a strict editor, only accepting proposals that score well under the causal distribution. Meanwhile, in parallel, the diffusion head brainstorms multiple next step drafts, conditioning on every possible outcome of the AR decisions, so you don't stall waiting for the verdict. A carefully designed attention mask lets both flows happen in a single forward pass. The result: you keep GPUs busy with parallel drafting, but the AR head guards quality. As long as the draft regions fit into unused token slots, the extra overhead is tiny. Training TiDAR is simple and data efficient because one model learns both behaviors with a hybrid attention mask. The mask is causal, where we need AR-style conditioning, and bidirectional, where diffusion needs to see more context for denoising. Crucially, the same batch teaches both heads. You compute an AR loss on the committed path and a diffusion loss on masked tokens in the diffusion region. Setting diffusion region tokens to mask during training does 2 things. It strengthens the denoising signal, the model consistently learns to recover masked content, and aligns training with inference, where those slots are indeed drafts. This joint training balances the objectives so the model becomes good at fast parallel proposing and reliable AR choosing without needing separate models or complex data pipelines. Here's the big idea of the figure. Modern GPUs don't scale latency linearly with a few extra tokens. There's a flat zone where you can stuff more tokens into a forward pass, and the runtime barely changes. Think of a bus that has empty seats. Adding a few more passengers doesn't delay departure. Those are the free and cheap token slots. As the prefix KV cache gets longer, attention gets heavier, and you eventually hit the compute-bound region. Now, every extra token costs real time. TiDAR exploits the flat zone. It packs parallel drafting and sampling into those free/cheap slots, so you get many candidate tokens for almost free within one pass. Only when you cross the saturation point does latency grow. This hardware-aware trick is why TiDAR can brainstorm broadly without paying a proportional time penalty, then still finalize precisely. The punchline numbers. TiDAR 1.5b matches the quality of a standard autoregressive model while delivering a 4.71x boost in tokens per second. The 8B version hits about 5.91x with only minimal quality loss. Why does that matter? Because throughput is what users feel, how fast text streams out. Traditional diffusion models trade speed for quality. Classic autoregressive models trade quality for speed. TiDAR gets both by drafting many options in parallel using those free token slots, then locking in the final token with an AR-style decision, all in a single pass. So the system drives the GPU harder without sacrificing coherence. The result is a practical speedup, not a theoretical one. The model produces more tokens per second with quality that's competitive with or indistinguishable from the AR baseline. Speculative decoding frameworks differ along two crucial dimensions: how strong the drafter is, and whether drafting and verification can run in parallel. Many classic methods use a small separate drafter that's fast but weak, good for proposing a few easy tokens, but it collapses on harder context. Worse, verification often runs after drafting, creating a stop-and-go pipeline. TiDAR flips this script. Its drafter isn't a tiny sidekick. It leverages the base model's capacity to produce high-quality drafts. And the drafting is structured to coexist with verification in a single forward pass, so you avoid the sequential bottleneck. The net effect: stronger proposals, fewer rejections, and far better hardware utilization. That's the core advantage over classic speculative decoding, APD-like approaches, and multi-token predictors that still require extra passes or weaker drafting. Why do these two axes matter? 1. Shared versus separate drafter. A shared, high-capacity drafter sees the same features and heads as the base, so it proposes tokens that the base model is actually likely to accept. Fewer wasted guesses, higher hit rate. A separate small drafter needs extra layers/heads and often goes off distribution, leading to more rejections. 2. Parallel versus sequential with verification. If drafting and verification happen in lockstep within the same pass, you remove pipeline stalls. Sequential verification means idle compute and added latency between propose and accept/reject. TiDAR's design lands in the sweet spot. High-capacity drafting that's synchronized with verification, giving you both speed and reliability. Diffusion language models promise speed by generating multiple tokens at once. In theory, great. In practice, pushing more tokens in parallel often hurts quality. Why? Because those tokens don't fully condition on each other. Each is like a guess made without hearing everyone else's answer. The more you parallelize, the looser the coupling, and errors creep in. Local inconsistencies, weaker long-range coherence, and a tendency to fall back on safe, generic continuations. Many open-source diffusion LMs quietly end up decoding one token per step to keep quality high, which erases their parallel speed advantage. This is the core tension TiDAR addresses. It uses diffusion-style parallel brainstorming to explore options fast, but then applies an autoregressive, context-aware selection to commit to the final token. You get the breadth of parallelism without the usual coherence tax. Here's the crux. When diffusion-style language models try to spit out multiple tokens at once, they usually treat each token's choice as independent. That's like asking 5 people to write the next 5 words without letting them talk to each other. Faster? Sure. Coherent? Often not. You see it in practice. Even moving from 1 token to 2 per step can noticeably drop quality. Why? Because sentence-level constraints, agreement, style, logic, live in the dependencies between tokens, which this independence assumption throws away. To fight this, recent methods tweak how compute and probability are handled. E2D2 splits the work. A heavy encoder focuses on clean tokens, while a lighter decoder handles the noisy ones, trying to spend compute where it matters. EGLM adjusts the model's scoring so the sampling process better matches training, reducing that classic training-sampling mismatch that causes off-by-one style errors. The big picture. Parallelism is tempting, but without modeling token interactions, coherence suffers. These methods try to claw back that lost structure. Caching is the secret sauce behind fast autoregressive decoding, but diffusion models break it. In AR, every new token only looks backward, so you can cache past keys/values and reuse them. Huge speed wins. Diffusion uses bidirectional attention while denoising, so future and past positions talk to each other. Your past cache stops being correct the moment the future changes. Workarounds try to bend the rules. Fast DLLM chunks the sequence into blocks, caching the prefix and sometimes a suffix, while it denoises the current block. DKV cache selectively delays which tokens to cache, aiming to keep quality while still saving compute. Block diffusion goes semi-autoregressive. Decode block by block, AR across blocks, but fill the inside of a block with diffusion. Even with exact caching, though, you inherit the original tension. Inside each block, you want parallel speed, but that reintroduces token independence and hurts quality. Net, clever caching helps, but doesn't fully resolve the parallelism vs coherence trade-off. Speculative decoding speeds things up by having a smaller drafter guess several future tokens, then the big model checks and accepts or rejects them. The catch: if the drafter's guesses are weak, the acceptance rate tanks, and you lose the speed up. So newer methods tap into the base model's hidden states, its rich internal features, to guide drafting. Medusa adds multiple heads on those states to predict branches of future tokens. Eagle and DeepSeek 5.3's multi-token prediction stack extra autoregressive layers to push further ahead, but two bottlenecks remain. First, capacity. A small drafter, even with borrowed hidden states, still isn't the full base model, so its guesses lag in quality. Second, sequencing. Many of these drafting modules are themselves autoregressive and run sequentially relative to verification, which limits parallelism. That means poor compute density. Your GPU isn't saturated because you're still waiting on steps in a chain. Seen through the speculative decoding lens, TiDAR's big move is collapsing drafter and verifier into a single model and a single forward pass. That unlocks 3 wins. 1. Capacity. Your drafter is the base model itself, so candidate proposals aren't handicapped. 2. Parallelism. The drafting phase uses diffusion, so you can brainstorm across many masked positions at once, not just the last token like typical MTP approaches. 3. Zero handoff overhead. Drafting and verification happen together, so you avoid the sequential accept/reject loop. Practically, this sidesteps the classic acceptance rate bottleneck and lets you flood the GPU with parallel work. You get the creativity of wide, parallel drafts and the discipline of context-aware selection, without ping-ponging between 2 models or 2 passes. Method-wise, the backbone is trained to do 2 things at once in a single forward. Understand the whole sequence jointly, the autoregressive, context-faithful view, and understand each position's standalone possibilities, the diffusion marginal view. Think of it as teaching the model both how to imagine many plausible futures in parallel and how to commit to a coherent next step. At inference, TiDAR turns this into self-speculation. The same model first thinks in diffusion mode to cheaply explore candidate tokens across positions, then talks in autoregressive mode to finalize tokens with full context. Because both behaviors live in one network and one pass, you get parallel drafting without losing the AR guardrails. The result: high throughput from parallel brainstorming, high quality from context-aware selection, plus training/inference tricks to keep it efficient on real hardware. Here's the rhythm of TiDAR in one go. First, it verifies the tokens it drafted in the previous step and decides how many of them to accept as the new prefix. Think of that as a quick quality check. Keep the solid prefix, drop the shaky tail. At the same time, it has already prepared multiple proposals, candidate continuations, for what comes next. Once the accepted prefix is known, TiDAR instantly picks the matching proposals and locks them in. Any candidates that don't fit the accepted prefix get rejected. Crucially, all of this happens in a single forward pass. Verify last step, select what fits, and pre-draft the next step. The causal part keeps a reliable, catchable context, KV cache, for fast reuse. But if a token is rejected, its cache is evicted to stay consistent. This is how TiDAR fills the free token slots on the GPU, verifying and pre-drafting concurrently so nothing sits idle, turning the usual stop-and-go generation into a smooth assembly line. The architectural trick is mask switching within one pass. Clean, already accepted tokens use causal attention, classic AR behavior, so the model reasons left to right with a trustworthy context that can be cached. Meanwhile, the to-be-drafted positions sit in a special block that's bidirectional just within that block. That block bidirectional pocket acts like a brainstorming room. Draft tokens can see each other to form coherent proposals without violating the causal boundary with the prefix. After verification, TiDAR selects the proposals that match the newly accepted prefix and discards the rest. The causal tokens, KV cache, is saved for speed, but if selection rejects some tokens, their cache entries get evicted, so the model never builds on bad context. Net effect. In one forward, TiDAR both finalizes some tokens and prepares candidates for the next ones, keeping throughput high without losing the AR discipline that preserves coherence. Picture the sequence split into two zones: a causal zone, the solid, clean prefix, and a draft zone, a compact block of mask tokens. The causal zone can only look left. This anchors the model in real history, like standard language modeling. The draft zone, however, is bidirectional within itself. That means all draft positions can peek at each other during this one-step diffusion-style pre-drafting, helping them coordinate and avoid silly inconsistencies. It's like letting the next few words workshop together while still respecting the boundary with the true past. Labels like training mask and decoding mask just indicate how these zones are wired during learning versus inference. The key intuition: keep the prefix trustworthy and catchable, and give the draft block just enough internal communication to produce strong proposals in parallel. Training uses an appended block of mask tokens, e.g., length 3. Real tokens attend causally. Mask tokens attend bidirectionally within their block and can also see the prefix. This teaches the model both behaviors at once: AR for solidity, diffusion style within the block for parallel drafting. At inference, instead of rebuilding masks every time the prefix grows, TiDAR slices from a pre-initialized, reusable mask. It also reorders the prefix and the sampling draft region, so the same mask pattern keeps working step after step. Why care? Because reusing a fixed mask unlocks efficient kernels and avoids per-step graph surgery. The model can rapidly accept a new prefix, pick the right pre-drafts, and immediately populate the next draft block, keeping decoding parallelized and steady without mask bookkeeping overhead. Goal: make one backbone that runs both diffusion-style drafting and autoregressive verification in a single forward pass, so we can exploit those free GPU token slots. The solution is a hybrid attention mask, causal for the prefix, bidirectional only in the last block, the decoding block. This is a deliberate tweak to block diffusion. Instead of many bidirectional blocks, only the final block gets it. Everything before remains causal. Why is that powerful? First, The causal prefix preserves the chain-factorized joint distribution, so we can do proper AR-style likelihood and principled rejection sampling with quality guarantees. Second, it means we can keep training with the standard next token prediction loss on the prefix, leveraging all the usual AR pre-training machinery and efficiency. Meanwhile, the bidirectional last block gives us fast, coherent pre-drafts in parallel, put together. AR reliability where it matters, diffusion speed where it's safe, all in one pass. 2 training signals matter here: next token prediction, NTP, and diffusion-style denoising. NTP is dense. Every position teaches the model something, while diffusion loss is typically sparse because it's only applied to masked, corrupted tokens. There's also a trap with diffusion-style bidirectional attention. If you try to train on the prefix with full look-ahead inside a block, you leak the correct labels into the inputs, making the loss meaningless. The takeaway: pure diffusion can't supervise the prefix cleanly and wastes potential supervision, while NTP can. TiDAR's move is to combine both signals in a way that avoids leakage and makes better use of every token. Think of it as getting both what comes next, AR, and what should be here, diffusion feedback, without tripping over label leakage. Here's the training layout. They effectively double the sequence by appending a corrupted copy to the original. The first half is the causal autoregressive zone. Classic next token prediction with labels shifted by 1. You only see the past. The second half is the diffusion zone. Bidirectional attention predicts each position from its neighbors, and labels stay aligned. You predict the token at the same spot. Traditional diffusion methods add random masks to decide which tokens are corrupted, following a schedule. This setup lets the model learn 2 complementary skills simultaneously: precise step-by-step continuation in the AR half, and parallel fill-in-the-blank reasoning in the diffusion half. The doubling is what gives the model both perspectives in one batch, a clean way to teach it to draft in parallel and then decide with context. Key simplification: mask every token in the diffusion section. No fancy masking schedules, no guessing rates. Why is this great? First, it makes the diffusion loss dense. Every position contributes signal, not just the randomly corrupted ones. Second, it fixes the balancing headache. In classic diffusion, the number of supervised positions varies per example, but NTP always has the same count. That mismatch makes it hard to weight the 2 losses fairly. With full masking, both losses sum over the same number of positions, so a single scalar weight cleanly trades off AR versus diffusion. Third, it unlocks one-step diffusion at inference. Because the model was trained to predict all masked positions in one go, it can draft an entire block in parallel without multi-step denoising. That's a huge practical speed win and a perfect fit for GPUs. Putting it together, TiDAR's objective is just a clean blend of 2 cross-entropy losses, an autoregressive loss on the causal part and a diffusion-style loss on the fully masked bidirectional part. A single weight scales the diffusion term, so you can dial quality-speed trade-offs. The beauty is in the symmetry. Both losses span the full sequence length, so the balancing is straightforward and stable. Conceptually, you're teaching one model 2 complementary behaviors, draft broadly in parallel, then decide precisely with context, and training them side by side so they cooperate at inference. Intuitively, the loss says, sum the AR next token prediction over the causal half, and sum the diffusion-style predictions over the masked half. Then blend them with a knob that controls how much you value parallel drafting versus stepwise accuracy. Because the diffusion side masks all positions, its loss is as dense as the AR side. That symmetry is what enables clean, stable co-training. Both halves learn at the same resolution and contribute comparable signal. The effect is a model that's fluent in 2 modes. It can rapidly sketch many plausible continuations in parallel, and then verify them with AR precision. The weight, alpha, is your balance control between speed, diffusion drafting, and precision, AR verification. Both losses are standard cross-entropy, but computed under different attention patterns: causal attention for the clean AR half, and bidirectional attention over the masked half. That separation ensures no label leakage while giving the diffusion branch the global context it needs to predict each position. In practice, tuning alpha lets you nudge the model toward more aggressive parallel drafting or tighter AR faithfulness, depending on your latency and quality targets. Generation speed isn't just about fewer steps. It's a three-way balance: how many forward passes you take, how many tokens you produce per pass, and how long each pass takes. Many methods improve one axis but hurt another. Diffusion models parallelize tokens but need multiple denoise steps. MTP predicts multiple steps but fights consistency. Speculative decoding reduces AR work but adds coordination overhead. TiDAR's goal is to jointly optimize the whole pipeline. It fuses diffusion-style parallelism, high tokens per step, with AR-level quality, keeping latency per step low and compute highly utilized. The result is a single model designed to draft broadly and decide accurately in one smooth loop, instead of stitching together separate systems with bottlenecks. Here's the generation dance. Step 1. Given the prompt, the model uses causal attention to anchor context, then drafts a whole block of candidate tokens in parallel using bidirectional attention. Think of this as the model's marginal guesses without committing to order. Step 2. It verifies those candidates autoregressively. Moving left to right, it checks whether each drafted token matches what the AR joint distribution wants. Matching tokens are accepted. The first mismatch stops acceptance. That preserves AR quality. Crucially, to avoid stalls, the model also pre-drafts the next block in parallel, conditioned on every possible acceptance length, 0, 1, 2. So regardless of how many tokens you accept this step, you already have the right drafts for the next step. This self-speculative loop keeps the GPU busy, amortizes verification over big parallel drafts, and retains AR coherence, fast and faithful. Read this plot like a speed vs quality map. The x-axis is how much faster decoding is than a same-size autoregressive baseline. The y-axis is task accuracy on code and math benchmarks. Same color means same model size. Different markers are different methods. The headline, TiDAR points, sit further right, faster without sinking lower, worse quality. That's the dream. More tokens per second while keeping accuracy steady. You'll also notice a clear knob. TiDAR's training block size shifts where the point lands. Bigger blocks push speed rightward, with only a mild quality trade-off. Block diffusion, by contrast, tends to pay more in quality or computational cost as it pushes speed. Those tokens per step annotations reflect how denoising steps drive cost. Speculative decoding boosts speed but hits overhead and rejection limits. TiDAR redraws the Pareto frontier at both 1.5B and 8B, the one-pass draft and verify pipeline scales, not just a small model trick. Classic diffusion uses multiple denoising steps. TiDAR drafts in just one. Why does that hold up? Because the draft doesn't need to be perfect. It just needs to be good enough that the autoregressive verifier accepts most tokens. Think of diffusion as a rapid brainstorm and AR as the careful editor. One strong brainstorm pass is plenty if the editor immediately follows. To train for that, TiDAR makes the drafting challenge maximal. It fully masks the diffusion section, so the model learns to generate plausible tokens from scratch in a single leap. That forces it to pull in global bidirectional cues and produce draft tokens with high acceptance rates. The payoff is big. collapse many diffusion iterations into one forward pass, preserve coherence through AR verification, and slash latency without fiddly denoising schedules or step tuning. Blending diffusion and autoregressive learning only works if their losses are on comparable scales. TiDAR ensures that by fully masking the corrupted draft half during training, so the diffusion logits and AR logits face similar difficulty and end up with similar variance. With that natural balance, you can set the loss weight to a clean alpha equals 1 and let the model learn both behaviors, parallel drafting and causal verification, without one overpowering the other. Practically, that means less hyperparameter babysitting, more stable training, and a predictable speed-quality trade-off. If you ever need to tilt towards speed or precision, you can still adjust the weight, but the default just works. Deployment speed is mostly about never redoing work. TiDAR designs inference so each step sends the same number of tokens with the same attention pattern. They pre-build a single block attention mask and then slice it every step. No per-step recomputation, so it plugs neatly into efficient kernels like flex attention. Even better, unlike typical diffusion, TiDAR supports an exact KV cache. All tokens computed with causal attention are cached once and reused. If the final sample is shorter than the draft window, they simply evict the extra tail. No KV is ever recomputed. That's a stark contrast to many diffusion-style decoders that either lack exact caches or pay a heavy recomputation tax. The result feels like AR speed caching plus diffusion-style parallel drafting, tight GPU utilization, minimal overhead, and faster than block diffusion decoding without cache gymnastics. No inference time fiddling required. There are no diffusion steps, thresholds, or schedules to tune. You get predictable speed and quality by default, with optional switches elsewhere if your application wants a different trade-off. Here's the ground truth for how they evaluate TiDAR. They start from strong autoregressive AR bases, QN 1.5b, 4b, 8b, and do continual pre-training, so gains aren't coming from data tricks, but from the decoding/training design. For quality, they test real unforgiving tasks: coding, human eval, MBPP, and math, GSM 8K Minerva, where a single wrong token fails the whole answer, plus knowledge and common sense benchmarks for breadth. For efficiency, they report two practical numbers: tokens per model forward, NFE, and tokens per second on a single batch. NFE is the right lens for TiDAR because it drafts multiple tokens in one pass, so how many tokens per pass directly captures its core advantage. Token/SEC shows actual latency. Using LM evaluation harness standardizes configs so results are apples to apples. Together, these metrics tell you, does it stay accurate on hard tasks, and how fast is it in the real world? They benchmark against strong AR baselines, Llama, Smol LM, QN, and Diffusion LLMs, Dream, Lada, plus their own re-implementation of block diffusion under the same recipe. This keeps comparisons fair. Same sizes, similar training, different decoding brains. Training choices here matter because they reveal robustness, not just leaderboard tuning. For the 1.5B model, they continually pre-train on 50B tokens. For 8B, 150B, both realistic scales. They sweep block sizes, 4, 8, 16. That block size is the draft length per pass. Larger blocks promise more speed but raise the bar for coherence. So this sweep exposes the speed-quality trade-off TiDAR must navigate. Everything else is intentionally standard. Cosine LR schedule, common optimizer, 4K context, BF16, gradient checkpointing. No exotic tricks. They run both training and inference in the same precision and focus ablations on 1.5B to show where the gains come from. The headline, with a simple, repeatable recipe, TiDAR scales to 8B and still delivers speedups. Evidence the method itself, not hyperparameter magic, is carrying the results. To judge generative quality fairly, they zoom in on coding and math. Why? Because these tasks have crisp, automatic pass/fail metrics. You can't hand-wave a half-right sentence here. The program must run. The proof must compute. This makes them perfect stress tests for a model that drafts in parallel. Any small incoherence gets punished. They pit TiDAR against both AR models and a diffusion-style baseline, block diffusion, across two sizes, so we see both ends. Can TiDAR match AR-level precision while being faster? And can it avoid the typical diffusion pitfalls, like losing logical consistency, when the pressure is on? The table they reference is essentially checking. Does the hybrid actually deliver on its promise where it's hardest to hide mistakes? The key number, tokens per forward pass, NFE. For approximately 1.5B, 1.7B models, TiDAR stays competitive in quality while producing about 7.5 tokens each pass. So one pass equals a short phrase, not a single token. At 8B, it nudges that to approximately 8.25 tokens per pass with barely any quality drop. That's the hybrid paying off. Diffusion drafts multiple tokens. The AR path keeps them honest. They also try two decision modes, trust AR versus trust diffusion. Think of it as who gets the final say when there's disagreement. As capacity grows, the diffusion drafts get sharper, so letting diffusion lead often helps, especially in math, where parallel brainstorming can explore multiple steps and AR verification prunes errors. The big picture. Larger models unlock more confident, useful diffusion drafts, which TiDAR can safely accept without losing rigor. Against pure diffusion LLMs, Dream, Lotta, Block Diffusion, TiDAR consistently wins on quality. There's a reason. Diffusion LLMs often have to decode one token per pass to keep coherence, because their parallel predictions don't see each other's finalized choices, so errors compound if you go faster. TiDAR sidesteps that trap. It drafts in parallel, but then uses an AR lens to adjudicate and stitch those drafts into a coherent continuation. So it captures diffusion's speed without paying the usual coherence tax. When they compare, they even let diffusion baselines use their safest mode, one token per pass. Yet TiDAR still comes out ahead, showing the hybrid mechanism isn't just faster, it's fundamentally more reliable for structured text. Bottom line, TiDAR delivers AR-like accuracy with diffusion-like throughput. If your app cares about latency, coding assistance, interactive agents, on-device generation, this trade-off is exactly what you want. More tokens per pass without the logic wobble that usually comes with parallel decoding. Measuring likelihood is straightforward for AR models, next token probabilities, but it's messy for diffusion LLMs. Why? Their training corrupts tokens and teaches the model to denoise masked positions. So at evaluation time, you're not scoring the full sequence log likelihood. You're scoring probabilities on a subset of corrupted tokens under a particular masking scheme. Change the corruption or mask, and the likelihood changes, making numbers hard to compare across papers. This is why diffusion LLMs often skip clean perplexity-style reporting. TiDAR helps here because it retains an AR pathway. You can compute standard likelihoods while still benefiting from diffusion-based drafting. In other words, it gives you a common currency, AR likelihood, for fair comparisons, without giving up the speed tricks that make diffusion attractive in the first place. What this table really shows, TiDAR can keep coding and math quality in the same ballpark as strong autoregressive baselines while moving multiple tokens per model forward pass. The numbers in parentheses are the average tokens accepted per forward, TNFE. Think of it like an assembly line that approves 7 to 10 tokens each cycle instead of 1. That's where the speedup comes from. The striking part is the quality doesn't crater like in many diffusion-style systems. Why? TiDAR does the fast, parallel brainstorming with diffusion, but still lets an autoregressive check make the final call in one combined pass, so coherence stays intact. The two decoding flavors, TrustAR versus TrustDiff, are simply a dial on that final call. Lean more conservative, quality, or more aggressive, speed. Across both small, approximately equals 1.5B, and larger, approximately equals 8B, models and across coding, Human Evil MBPP, and Math, GSM8K, Minerva, Math, TiDAR's accuracy tracks the AR bases closely, yet its TNFE shows real throughput gains that diffusion-only methods struggle to convert without losing coherence. There's a long-standing headache in evaluating diffusion-style LMs. Multiple-choice likelihood scoring is easy and standard for autoregressive models, but diffusion models don't naturally assign token-by-token likelihoods. People end up using Monte Carlo tricks that are slow and can be hard to compare fairly. TiDAR sidesteps this. Because it has a true AR mode baked in, it can compute the same normalized likelihoods as a regular LLM, no approximations. That means apples-to-apples comparisons on standard MC benchmarks, and the scores actually reflect generative quality because the final selection step is autoregressive. Bonus. It does this with a single model evaluation, single NFE, so evaluation is fast too. The upshot. With TiDAR, you don't have to choose between a fast generator and a model you can't fairly evaluate. You get diffusion's speed advantages and AR's clean, comparable likelihoods. The efficiency benchmark is set up to isolate real algorithmic speed, not system quirks. They compare three families: plain AR decoding, speculative decoding, Eagle 3, and diffusion-style generation, block diffusion, against TiDAR. All use identical KV cache support and run on a single H100 with batch size 1 and real prompts. Why this matters? KV caching and request shape can easily bias results. If one method can't reuse caches the same way, it's unfairly slower. By equalizing caches and hardware and using downstream-style prompts, the comparison focuses on what we care about: how many tokens per second you actually get for real tasks. This setup highlights whether TiDAR's draft and parallel verify once design translates into wall clock gains over the strongest alternatives, not just theoretical flop savings. Here's the punchline of the speed tests. TiDAR delivers multi-X speedups, around 5-fold, over equally sized AR baselines while keeping similar task performance. Against block diffusion, it hits a better efficiency-quality trade-off, meaning it turns parallelism into speed without the usual coherence tax. And compared to state-of-the-art speculative decoding, Eagle 3 open weights, TiDAR shows that diffusion-based hybrids can actually surpass those efficiency gains. Important nuance. Speculative decoding guarantees identical outputs to the base model. TiDAR isn't trying to match bit for bit. It's optimizing for fast, high-quality generation. Two helpful concepts. Acceptance rate, TNFE, is how many tokens you approve per model call. Conversion rate, T-second, is how well that theoretical gain turns into real throughput. TiDAR's acceptance rate is high, and its conversion rate is even better because drafting and sampling happen in one forward pass. No second model, no sequential verification bottleneck. All methods here could go faster with deeper systems work. Custom kernels, smarter KV cache layouts, and better scheduling. The point of these benchmarks is that TiDAR's speedups already show up under a fair, shared setup. In other words, the gains come from the algorithmic design. With the usual systems engineering on top, you should expect even more headroom. This table is the "does it actually stay smart" check. It compares TiDAR against regular autoregressive models and diffusion-style baselines on knowledge and common-sense tasks like MMLU, ARKey, HelloSwag, PIQA, and Winogrande. The big picture. At 1.5 B scale, TiDAR sits very close to its AR base and clearly ahead of block diffusion, meaning the parallel drafting doesn't wreck coherence. At 8B, it's even more striking. TiDAR matches or beats the strong AR baseline on several benchmarks, e.g., High-Throughput, PIQA, Winogrande, while staying competitive on the rest. That's the promise in action. Parallel speed with AR-level judgment. If diffusion-style methods typically pay a quality tax, TiDAR largely dodges it by drafting in parallel but deciding with AR context. So the takeaway from this table, you can get multi-token per pass throughput and still keep the reasoning and factual chops that matter on standard benchmarks. Likelihood matters because it's how we score text, re-ranking candidates, doing perplexity-style evaluation, and comparing models apples to apples. Pure diffusion LMs struggle here. They need Monte Carlo tricks to approximate likelihood, which is slow and noisy. TiDAR sidesteps that. Thanks to its architecture, it can evaluate likelihood like a normal autoregressive model using a causal mask. That means faster, cleaner, and standard compliant scoring without special sampling loops. It also makes the comparisons fair. Diffusion baselines are evaluated with MC, many steps, extra compute, while TiDAR just computes likelihood natively. Bottom line, you get both the decoding speedups from parallel drafting and the practical usability of AR scoring, which is rare in diffusion-flavored approaches. Here's the cleanest way to judge an architecture. Train everything under the same recipe, then plot the Pareto frontier between quality and speed. Speed here is tokens per neural function evaluation, how many tokens you get per forward pass. In that controlled setup, TiDAR lands near the frontier, much faster than plain AR, and noticeably higher quality than block diffusion at similar speeds. Even with just 50 B tokens of training, it's already competitive. There's still a small gap versus heavily fine-tuned AR models, which likely comes from TiDAR needing some adaptation time to master the hybrid drafting verification behavior. The authors suggest more data would close that gap. The key insight: when you hold the training conditions fixed, the architectural win shows up clearly. TiDAR trades speed for quality far better than a diffusion-only approach, while preserving most of the AR sharpness. There are lots of decoding hacks for faster generation. Fix how many tokens you produce per step, make it dynamic based on uncertainty, set confidence thresholds, or decode left to right within each block. These all help, but they force you to pick and tune hyperparameters, and they often trade stability for speed. TiDAR's advantage is that it blends diffusion-style parallelism with AR-style decision-making inside one model, so it gets both the throughput and the quality without per-task tuning. In practice, that means fewer knobs to fiddle with and more consistent behavior across datasets. The comparison shows that while other strategies can be fast, they either need careful calibration or sacrifice coherence. TiDAR bakes the coordination into the model itself, so the how many tokens to draft and accept decision is learned rather than micromanaged by decoding rules. A subtle but important design choice. They avoid label shifting in the diffusion drafting stage. Why care? Label shifting can create a mismatch where the draft head tries to predict a token before it actually knows the final accepted value from AR, which injects inconsistency and hurts quality. By not shifting, the model can pre-draft the next block in parallel without waiting for AR to finish, and the masks stay logically consistent. The trade-off: the very first position in each block, and the AR output there, is tied to a fixed denoising step, which slightly constrains how that position is predicted. But the payoff is big. True overlap between drafting and verification, so the GPU stays busy and the pipeline stays coherent. In short, no label shift lets TiDAR pre-draft safely and efficiently, with only a minor controlled constraint at block boundaries. This multi-panel plot is the "does it actually hold across tasks" check. You're looking at coding, human evil, MBPP, plus variance, math, GSM 8K strict, and an average. The key curves are block diffusion baselines, R method with random mask, and R method with full mask at different block lengths, BL4, BL8, BL16. 2 takeaways. First, TiDAR sits above block diffusion across the board, meaning for a given compute budget, you get better accuracy. Second, the full mask strategy consistently beats random mask. Why? It matches the inference regime better, so the diffusion drafter learns to operate without peaking at partially clean tokens. As block length grows, 4 right pointing arrow, 8 right pointing arrow, 16, you're asking the model to draft more in one go. That boosts throughput, but gently pressures quality. The plots show that even with longer blocks, TiDAR stays competitive with AR fine-tunes, while delivering many more tokens per forward pass. Bottom line, the speed-quality trade-off is favorable and robust across tasks. Pareto frontier equals the best you can do on quality for a given efficiency, and vice versa. This figure compares plain AR, fine-tuned AR, block diffusion at various thresholds, and TiDAR at different drafting lengths, all with the same training recipe at 1.5B scale. TiDAR defines the best frontier. For the same number of network evaluations, it achieves higher accuracy. For the same accuracy, it yields more tokens per forward pass. Crucially, it approaches the quality of fine-tuned AR while producing multiple tokens per NFE, which AR can't do without sacrificing coherence. Think of it as moving the entire curve outward. You don't just win at one point, you dominate the trade-off region. That's the practical value. Whatever your latency or cost budget, there's a TiDAR operating point that beats block diffusion and standard AR. What does TNFE mean? Tokens per network, forward pass, higher is faster. The table contrasts 2 families of ways to get more TNFE. 1. Confidence-based batching. Keep accepting multiple tokens in one go if the model looks confident. As you relax the threshold to push TNFE up, quality slides hard. Errors compound because once you accept a wrong token, every subsequent step builds on it. 2. TiDAR's draft and verify. Generate multiple candidates in parallel drafts. Then use an autoregressive check to accept only what fits the context. As you increase drafts, 4 right pointing arrow, 8 right pointing arrow, 16, TNFE climbs from roughly 3.5 to nearly 7, yet quality stays near or above strong AR baselines across human evol, MBPP, and GSM 8K. The intuition, the diffusion drafts explore in parallel, but AR verification filters out bad paths before they contaminate the sequence. So you harvest speed without letting errors snowball. The sweet spot often lands around 8 drafts. Strong speed up with minimal quality trade-off. At each position, the model has 2 opinions, the autoregressive head and the diffusion drafter. Both produce scores over the next token. Which one should we trust when we verify and accept tokens? That's the practical question. If these two heads are well aligned, you should get similar probabilities for the correct token. If they diverge, your verification gate decides whether to slow down, be picky, or speed up, be permissive. So the design challenge is, can we train the model so the two heads agree most of the time, letting us use either or even a blend without hurting quality? Their solution is to blend the two opinions before sampling, like asking two experts and taking a weighted vote. One weight leans toward the AR head, the other toward the diffusion head. Conceptually, this does two things. First, it calibrates trust. If the drafter is strong, you can lean more on it. If you want more conservatism, nudge toward AR. Second, it serves as a consistency test. If both heads learn the same distribution, the weight won't matter. The blend in either head alone will agree. This mixture is used at verification time. We compare the blended choice against the drafted token. If they align, we accept and move fast. If not, we slow down and correct. It's a simple, tunable gate for balancing speed and reliability. When they sweep the blending weight and even change how the two heads were balanced during training, performance stays stable. That's the punchline. The heads learn to agree. In other words, the model isn't brittle to which logics you use for verification. Assign the training tied the two behaviors together. The quality-speed trade-off then comes primarily from the AR rejection step itself. You go fast by proposing many tokens in parallel, and you stay accurate by only accepting what the AR gate blesses. So it's not that the AR head is smarter and doing all the heavy lifting. It's that the acceptance mechanism enforces coherence, while the diffusion drafts keep the GPU busy exploring good candidates in parallel. Full mask training is about matching the training signals to what the diffusion drafter actually sees at inference. During inference, drafting is one step. The drafter never gets partially clean future tokens. It works from masked positions. So in training, instead of feeding it partially revealed tokens, which leak hints and create a mismatch, you give it fully masked inputs on the draft side. This forces the drafter to learn how to propose tokens purely from the context and its internal coordination, just like it will at test time. Benefits: better train test alignment, less label leakage, and more stable drafting across longer blocks. That's why the hours full mask variants outperform random mask in the plots. The drafter is practicing the exact game it will play later, which tightens AR diffusion agreement and preserves quality even as you ramp up drafting length for speed. What happens if you lean more on the AR head or the diffusion head during sampling? This figure shows that TiDAR stays remarkably stable either way. As you shift the trust ratio between AR and diffusion outputs, performance remains nearly flat, and different loss weight choices during training lead to similarly robust curves. In short, the model is balanced. Either head can guide sampling without a noticeable hit to quality or speed. Takeaway: you can base acceptance on either AR or diffusion predictions and still get comparable quality and speedups, thanks to balanced training and a strong drafting model. Why did changing the masking pattern matter? Using full masking during training aligns behavior with how the model drafts at inference, which reduces train-test mismatch. It also supplies denser learning signals for the diffusion part and makes loss balancing easier after normalization. As Table 5 shows, this translates into consistent quality gains, especially on coding benchmarks, and it even lets you flexibly choose which head's predictions to trust for autoregressive rejection sampling. Do the numbers back this up? Yes! Switching from random corruption to full masking boosts accuracy across HumanEval, MBPP, and GSM-8K with the biggest gains on coding tasks. The parentheses report an efficiency metric, AVGTNFE, which also improves under full masking, meaning more tokens generated per model evaluation. In short, full masking raises both quality and throughput, compared to the other masking strategies. What about batching? Although results focus on batch size 1, TiDAR can scale. You can adjust the drafting block length at decode time to match different compute budgets, and the method remains competitive in flops per token. And long contexts? The approach isn't inherently limited compared to standard AR models. The current training setup doubles sequence length by appending mask tokens, which makes long context training heavier. Exploring more efficient extensions such as TiDAR-specific context parallelism is left for future work. Can it get even faster? Even with a straightforward PyTorch implementation using flex attention, throughput already improves substantially. Custom attention kernels and smarter scheduling could better exploit hardware-specific free token slots, pushing utilization and speed even further. What's the big takeaway? TiDAR blends two modes. It drafts many tokens in parallel with diffusion, the thinking phase, and then confirms them autoregressively, the speaking phase, in a single forward pass using a custom attention mask. By exploiting otherwise idle GPU capacity, the free token slots, it adds minimal latency while drafting more tokens. This delivers high throughput without sacrificing autoregressive level quality, and importantly, shows it can beat speculative decoding when latency is critical. The authors position this as a blueprint for future hybrid LLM architectures and inference methods.